In this problem, I'm going to talk about the use of the energy model with frictional forces of the drip pan. So in this situation, you have this block of mass m, and it has a velocity, and therefore kinetic energy, and we'll say here of 22 joules of energy as it comes sliding into this spring. It's going to make contact with it right when the spring is unstretched. So right now, right at this point right here, the spring is unstretched. Okay, I'll call it x initial. And there's friction here. The frictional force, we'll say, is 10 newtons. It's a 10 Newton frictional force acting between the block and the ground. So the question is, after this block comes and hits the spring, it's going to compress it, let's say to right here, x final, wherever that is, and it's going to come to a stop. First thing we want to find is what is the distance the object travels, x final, as it travels along this rough surface, encounters friction and the spring, and comes to rest right here. And then second, after it does stop at x final, what is its velocity after it comes back to x initial? Now it's going to be less than 22 because it's going to lose energy on the way to x final, and it's going to lose some more energy on the way back to x initial. So there's going to be friction that's going to be acting in both directions there. So we want to find these two things. So we have an energy model type problem with the drip pan. So let's analyze this problem. So step one, draw a reference line. There's no elevation change here. It's all on a flat surface, or kind of a flat surface here, as opposed to an incline. So I'm going to denote this surface here, right here, the reference line. Right there, that's RL. Step two, conservation of energy. So for part A, let's take a look at the energies involved. And I'll call this point here, point A, and I'll call this point B here, the initial and the final energies. So at point A, I definitely have kinetic energy, so I'm going to fill in this bucket here. There's no gravitational potential, in fact, for this problem throughout, because it's a level surface. Although if for an incline, you could include it, not a big deal. The spring is not stretched at this point. So this is, again, the relaxed position of the spring. So the spring is not stretched. When it comes to point B, it's come to a stop. There's no gravitational, and we do have spring energy here. And because there's friction on the way from A to B, the initial to final, we actually are going to lose some energy due to friction. There's going to be work done by friction right here. I'll draw that in there as that. So this is not a 100% efficient process. So this is our model. So for our equation, we're going to come up with, for part A, let's say here, for part A, we're going to have 1/2 mv squared, our kinetic energy, at point A. That's going to equal 1/2 kx squared plus the work done by friction, which is the frictional force, times the distance, although the distance is really x, so it's one and the same variable here. And then we're going to know the spring constant. Let's say the spring constant k is equal to something like 100 newtons per meter. Okay, so so for part A, we want to solve for x. So this quantity here is actually given. That's the 22. We don't have to plug in anything. It's just a straight 22 joules. And so we have an x squared term and an x term. So what this leads us to is a quadratic. So if I kind of rewrite this thing in the quadratic form, it's going to be 1/2 k x squared plus frictional force times x minus 1/2 mv squared, which is our 22, equals 0. So now we have it in quadratic form, and we can use the quadratic formula to solve for x. And then we can find the x value for the stopping point. So that's part A. So it's basically including an amount of energy lost in the work done by friction bucket here, including that on the right-hand side of the equation. Part B is now, after it comes to rest at x final, what's its kinetic energy back at this point? All right, without friction it'd be 22, but so we started with here 22, but because we lose energy back on the way back, it's going to be less than 22. So how do we analyze that situation? So let me go ahead and get rid of some of these energy buckets here, because it's a new set of buckets. Let me do some erasing here. So for a new situation, we need a new set of buckets. I'll erase this here. And erase this right there. Okay. And start anew. So let's start here with the new set of buckets. Okay, so if I start from, and I'll kind of jot the number thing down here, I'll go from, well, I'll just say from B to A. I'll go from B to A on the way back. So at point B, so I'll call this energy at point B equals energy at point A, because I'm going backwards here. I have, let's see, I have no kinetic because it's temporarily stopped. It's not on an incline or anything, so that doesn't change. And we do have spring potential energy. So I have that, which is 1/2 k x squared, and the x is what we just found from the previous part. When it goes back through point A, I'm going to have kinetic, so I'm going to have some of this. No gravitational and no spring, because at point A, if you recall, that's the unstretched position. So there's no, it's fully unstretched at this point. But again, we do have, because it's a rough surface, we're going to lose some more energy due to friction. So I want to have some energy loss there. So for part B, my equation becomes 1/2 k x squared, and again that x is from the previous part using the quadratic, equals 1/2 mv squared, which is the kinetic energy related to velocity, plus this frictional force acting again times x. So you can see here I have this potential spring, I have the kinetic, and I have the work done by frictional force. So in this case, I have an x term on both sides, but since I'm solving for this term here, I can simply say 1/2 mv squared equals 1/2 kx squared, which is the amount of energy stored in my spring, minus a little bit due to friction, minus because I'm bringing it to the side of the equation. And then I can solve for my kinetic energy, which you can see is going to be what I had before, minus a little bit, so less than. And then if I wanted to, I could actually solve for V. V equals, and I can multiply by 2 and divide by m and square root. I get an expression for V and a final velocity there. So that's an example of using the energy model with the drip pan, and all it comes down to is it's the same idea. You set a reference line, you define the energies at each point. So we did that for part A and part B. And on the way there, we lost energy due to friction. There was work done by friction. We included the drip pan. And on the way back, we lost more energy. And again, if this ever became attached to the spring, it'd go back and forth and back and forth and back and forth. And every motion of the spring, it lose energy and eventually come to stop, because all of the joules of energy, let's say the 22, would eventually come to this bucket and in the form of heat, light, probably heat because of friction, light or sound, and it come to a stop. So there's an example of the energy model with frictional forces.